Fusion by SveaShield is built for one of the hardest problems in real-world sensor operations, deciding what information can actually be trusted. In environments like airports and critical infrastructure, multiple sensors may report at the same time, but more detections do not automatically mean better awareness. Some observations may be duplicated, delayed, uncertain, contradictory, or simply wrong. The operator does not just need another dashboard. They need a system that can receive sensor data, validate it, normalize it, decide whether it should influence the live picture, and preserve the full evidence trail behind every decision. That is what Fusion does. This page is the operator dashboard, but the dashboard is only the visible layer. Behind it are almost 2,500 lines of compact Python code running a fast API backend that receives sensor data, validates it, converts it into one standard format, updates tracks, creates alerts, and keeps a full audit trail. The system is not hard coded for one demo. That should be much easier but much less valuable. Here, sensors, alert rules, trust policy, latency limits, measurement uncertainty, and site configurations are all separated from the core logic. That means that the platform can be adjusted for different customers, different sites, different sensor setups without rewriting the system at all. At the top, we see the current operational state. We have open alerts, active tracks, sensor online, coverage, redundancy, and audit events. These are live values from the backend API, so the dashboard is reading the current live system state. In the command tab, the operator sees what needs attention first. This is the triage view. These alerts are created by the rule engine. They can represent detections anywhere from restricted zone entry to unknown RF emitters without visual confirmation, duplicate detections, sensor agreements or suspicion, and even impossible movements. The key idea here is trust before fusion. Every observation is checked before it can reach the world model, especially for sensitive operations such as airports and other critical infrastructure. If something is duplicated, tampered with, suspicious, or physically impossible, the system does not use it for fusion at all. It still saves it for audit so it can review it later, but it does not contaminate the live picture. When I click acknowledge, this isn't just hiding the alert in the browser. It calls the backend acknowledgement endpoint and updates the alert state. The operator action here becomes part of the live system workflow. Now I'll open tracks. This is where we see the fused objects that the system is currently tracking. A track is not just one camera detection or one radar detection. It is built from accepted observation after they pass trust validation and normalization. When I select a track from the track dossier, the page loads the detailed track record. Now we can see the confidence, uncertainty, life cycle state, how many sensors contributed, and the evidence behind the track. This is where the system becomes much more than a visual dashboard. Confidence is explainable. The platform shows what affected the score, the original observation confidence, the reliability of the sensor, signal quality, multi-sensor confirmation, weather impact, and uncertainty. All of these are really important to get right, otherwise you only have a calculator that spits out an uncalibrated score of 1 to 100. For this hackathon, we decided to go the formal route, used by real platforms, so that operators can see precisely why the system trusts it. Here we also see the hypothesis and factors. These are from the fused track state and the rules around it. For example, the system can mark that something was confirmed by multiple sensors, that visual confirmation is missing, or that an object is moving towards a restricted zone. The provenance trail is critical. It shows which observations contributed to this track and which sensors they came from. If someone asks why this track exists, or why an alert was created, we can trace it back to the evidence. And all of these tables are, of course, exportable and implementation ready into almost any external system. Here in the Map tab, we see the operational picture on a real satellite map of Arlanda. The sensors are spread across the airport property, so the deployment is easier to understand visually. These are localized through real latitude and longitude coordinates, and any amount of sensor and location can be configured and labeled by the engineers and seeded with real-time weather and location-specific data, directly impacting the math behind the engine for object localization. Now, in sensors, where we can see the entire configured sensor network, each sensor has a type, adapter, capabilities, limitations, latency expectations, weather sensitivity, and trust state. This is important because different sensors speak different languages. A camera, radar, RF detector, weather station, or human report always have different input formats. The system here is also capable of accepting multiple formats for one sensor category. How, you may ask? The adapters convert each one into the same standard observation, contract, and new sensors can be added without rewriting the Fusion engine. The adapter readiness matrix also shows what is implemented now and what is a placeholder for future work. That makes the system credible by separating current capabilities from future extension that we can develop together with FLIR or other motivated partners. The system also handles connections and sensor latency, which are measured under real operations and tailored to the real site conditions. These may also be affected by weather without breaking the system. In alerts, we can inspect each alert in detail. Here, when I select an alert, I can see the related track or sensor, severity, evidence, rule evaluation, trust summary, and uncertainty. This means an alert is not just a warning message, it contains the information needed to review it and understand why it exists. Now, these explanations are also ready to be replaced or augmented by secure, well-scoped local LLMs that detect anomalies and interpret advanced connections between alerts. By using locations, timestamps, and historical patterns, the system can move beyond isolated detections and understand how events relate over time. For example, a cluster of detections across multiple weeks could be interpreted using environmental and operational context, helping operators identify recurring activity, imply meaning from patterns, and make more informed decisions in real-world operations. The Audit tab provides the full evidence timeline behind each detection. It shows when an observation was received, how it was trusted, whether it was normalized, whether it can update a track, and whether it created an alert. This gives operators a complete, reviewable decision chain from raw signal to final alert, which is crucial for accountability, investigation, and external reporting. The same audit tail is also ready to be exported via API to any external system. If I filter by layer, I can inspect the timeline with dropdowns, for example, for layers and event types to help us accurately isolate our desired result. And now, when I click Run Scenario Evaluation, the system shows all of the scenarios currently configured, including sensor agreements, impossible movements, and others. This is also completely configurable, and all of the values needed are easy to differentiate and understand. Now finally, in admin, we use this to prove the platform is fully functional, repeat video metadata, or reset the simulation state. This makes this demo repeatable and controlled on all devices without interfering with the future integration of real-life sensors, as it is passed to the Fusion layer, not coded into it. Now the key point is this. Fusion by SveaShield is not just showing that sensor fusion can work. It checks whether data should be trusted, blocks bad evidence before fusion, uses confidence and uncertainty, tracks where every decision came from, supports different sensor types, and exposes everything through APIs and exports. This is why we, as SveaShield, are all very proud to present this to you, the jury. And if you are interested in hearing about our research and progress timeline through version 1, 2, and now 3, please take a look at our main submission document. All of the work you see was planned and built by us during the hackathon. Thank you, and until next time.